Around the central atom, no lone pairs, only bond pair. So, how many number of electron pairs are there? Yes, bond pair is 2. That means a total of 2 electron pairs are there. CH4. As you can see here, there are 4 bond pairs and no lone pairs. So, the total number of electron pairs is 4. Due to the repulsions which is happening here, now the shape that they attain is called as square planar. Hello everyone, this is Ambali Unnikrishnan from the Department of Chemistry, Vidhyaashram Pre-University College, the Temple of Excellence, Mysore. So in last session, we discussed about bond polarity, dipole moment, and then we discussed in detail about Fajan's rules, right? So in this session, we will be discussing about the next theory, right? So the first theory that we studied, that is the approach towards the chemical bonding. The first one we studied was Coussin-Lewis approach, right? So the next one we are going to study today, that is valence shell electron pair repulsion theory, right? Under which we will be studying about the geometry of molecules with only bond pairs, right? And geometry of molecules with lone pairs as well. And then finally, we will be also discussing about the limitations of VSEPR theory. So let's begin with the first topic. So let's begin with VSEPR theory. As you can see, the valence shell electron pair repulsion theory, VSEPR theory. In short form, you can also write it as VSEPR theory instead of writing the whole name, right? So we studied that in Coussin-Lewis approach, how to represent the different atoms using Lewis dot structure, right? We studied in detail about the Coussin-Lewis approach. So when we were studying about that, we understood that from Coussin-Lewis approach to chemical bonding, they were not able to predict the shape of the molecule, right? They were able to represent the molecule, but were not able to predict the shape of the molecule. Then came this VSEPR theory, by which the shape of the molecules or the geometry of the molecules could be predicted. Now, with the help of what the shape of molecules can be predicted? It is based on the number of electron pairs present around the central metal atom. Now, based on what the shape of the molecules could be predicted? It is based on number of electron pairs which is present around the central atom. So, before studying about the different postulates about VSEPR theory, as the name says, it's valence shell electron pair repulsion theory, right? So, we know that what is happening. Let's consider 2 atoms here. Yes, there is a nucleus and there are valence electrons in the outermost shell, right? So, let's say in these 2 atoms, there are electrons present in the valence shell. So, what is happening when they are coming close together? We know that when atoms have to combine, they have to come closer, right? So, when they are coming closer, what happens? The electrons which is present in the valence shell of both these atoms, when they come closer, they start repelling, right? Because both the electrons are negatively charged, right? Let's take an example from your daily life itself, right? Let me say that if you don't like someone, what would you try to do? Yes, you try to repel them, right? If you're not liking someone, you don't go stand nearby them. Yes, you try to run far away from them, right? Same way, electrons are also having the same charge. That means they tend to repel each other. They don't want to stand near with each other. So what they do? They try to maintain a distance from them and they try to repel each other, right? We know that what happens? The same charge they repel and opposite charge attracts. So what happens when atoms come together? Right? The electrons start repelling each other. So, based on this repulsion, yes, the repulsion between the valence electrons, this theory was put forward, right? So, by Sidgwick and Powell in 1940, so the VSEPR theory was proposed by Sidgwick and Powell in the year 1940, and it's based on the repulsive character of electron pairs in the valence shell of the atom. As I said, in the valence shell, electrons will be present, right? Based on the repulsive character of these different electrons, yes, the VSEPR theory was put forward. Now we are going to study about the very important postulates of VSEPR theory, which is important, right? Yes. So let's begin with the first postulate. The shape of the molecule depends on the number of electron pairs, that is bond pair and lone pairs around the central atom, right? So what it depends on? The shape of the molecule depends upon the number of electron pairs. So the different types of electron pairs are bond pairs and lone pairs, which are present around the central atom. So how you can predict the shape of the molecule? If we know the number of electron pairs around the central atom, yes, the shape of the molecule can be predicted. So before moving on to that, what exactly is bond pair and lone pair? See, let's take the example of carbon dioxide. We have already studied the Lewis dot structure of it, right? So as you can see here, the carbon is having a double bond with this oxygen as well as double bond with this oxygen, right? And on the oxygen atom, yes, these 2 electrons are here and 2 electrons are here, as well as this oxygen, 2 electrons are here, right? Yes, so as you can see, these electrons which are present on the oxygen atom, they are not taking part in the bond formation, right? Only these electrons are taking part in the bond formation. So those electrons which are taking part in the bond formation, they form the bond pairs, right? So as you can see, 1, 2, 3 and 4. 4 bonds are there. So a total of how many bond pairs will be there? There will be bond pairs will be equal to 4. Right, yes. And what is lone pair? Those electrons or electron pairs which are not taking part in the chemical bond formation, right? So as you can see, this electron pairs which are present on oxygen atom, they are not taking part in chemical bond formation, right? So 1, 2, 3, 4, a total of 4 bond pairs and 4 lone pairs are also present in this case. Clear? So I hope you understood the difference between bond pair and lone pair. Yes. So the shape of the molecule depends upon how many number of bond pairs and lone pairs are there around the central atom. Right, that was the first postulate. Now second one, the pairs of electrons in the valence shell repel one another since the electron clouds are negatively charged. Yes, this is what we discussed now. Yes, since the electron clouds of the atoms are negatively charged, what happens? The pair of electrons in the valence shell, they repel each other. Each of these electron pairs, what do? They repel each other, right? Yes. Now moving on to the third postulate, right? The pair of electrons tend to occupy such positions in space that minimize the repulsion and maximize the distance between them. So as I said in the beginning, an example, if you are not liking someone, what do you try to do? You repel with them, right? Of course, you don't attract them, you repel them because you don't like them. So what do you try to do? You try to stay as far as possible as them. If you see them, you don't go near them, right? You run away from them. You stay as far as possible, right? You repel them to a maximum extent. Same case, the electrons, what do? The pair of electrons, right? One pair of electrons and the other pair of electrons, what do? They tend to occupy such positions. Yes, in the valence shell, they try to occupy such positions in space that minimize the repulsion. Okay. Yes, they try to minimize the repulsion and maximize the distance between them so that what happens? The stability will be maximum. So let's take the example of water molecule itself, H2O. Yes. So in this case, you can see on the oxygen atom, 2 lone pairs are there, right? This is one pair and this is one pair, right? One pair means 2 electrons, right? So 2 lone pairs are there and you can see 1 and 2 bond pairs. So that's also clear, right? So 2 bond pairs and 2 lone pairs are there. So what in this can you observe? Yes, these 2 lone pairs are trying to attain a position in space where they are repelled to the minimum. Yes, and the distance is maximum. So what do? They occupy these positions. Yes, so if they are coming a little bit towards this direction, now there is a bond here as well, right? So what do these molecules do that, or what do the electron pairs do that? Yes, they try to find positions in which, yes, the repulsion among them has to be minimum and the distance must be to the maximum. So they try to occupy such positions in space. Right. Now, multiple bond is treated as if it is a single electron pair and the 2 or 3 electron pairs of a multiple bond are treated as single super pair. Okay, now what is this? Multiple bond is treated as if it is single electron pair. So, in the previous slide, we discussed about, yes, CO2, right? Yes. So, as you can see here, there are one double bond here and one double bond here. which is a multiple bond, right? Double bond and triple bond are called as multiple bond. Yes, so multiple bonds, according to VSEPR theory, they are considered as single bond, right? So if I have to predict the shape of this particular molecule, what do I have to do? Yes, the number of bond pairs should be considered as 2, not 4, right? So as you can see here, even in the case, you can see 2 pairs here and 2 pairs here, which will give you a total of 4. But still, according to VSEPR theory, multiple bonds are considered as a single bond only. So 1 bond here and 1 bond here. So that will give a total of 2 bond pairs. Are there any lone pairs around the central atom? No, right? So the number of lone pairs will be 0. So what will be the total number of valence electron pairs? That will be 2 plus 0, right? That is 2 itself. Clear? Yes. So the multiple bonds, even in certain other molecules, we know that there are triple bonds present, right? So even in such molecules, if you are counting the number of bond pairs, what do you have to do? Instead of 3, it will be 1. So I hope it is clear. Multiple bonds are considered as single bonds. That is why it is not 4 there and it is 2. Yes, it is still a double bond present there, right? It doesn't become single bond. So according to VSEPR theory, we consider it in that way. I hope it is clear. Now moving on to the last one. The order of repulsive interaction of electron pairs. This is very important, right? It is lone pair interactions are greater than lone pair bond pair interaction, which is greater than bond pair interaction. Now what is this? We understood lone pair and bond pair, right? So let's take this water molecule itself. Yes, these 2 electron pairs that you can see here, they are called as a lone pair. And these are, yes, these 2 are the bond pairs, right? So the repulsive forces between the lone pair and lone pair will be the maximum. So as you can see, the lone pairs are present on the top of the oxygen atom. Yes, and they are able to move freely around the atom, right? As we know that lone pairs are not bonded with any other atom. They can move freely here. So their repulsion will also be the maximum, right? And in the case of bond pairs, what it is happening? It is actually the bond pair of electrons. They are getting bonded, like they are participating in the bond, right? So what happens? They can't easily move around because they are bound to someone. Right, some atom they are bound to. So what happens? They won't be able to move freely. Hence, their repulsion will be less. So that is why lone pair repulsion is more. And then lone pair and bond pair will be the least. Yes, so I hope it is clear. Yes. So now what we are going to do is, according to what and all we have discussed till now, the postulates of VSEPR theory, what did we understand? Yes, if we know the total number of valence electron pairs, we can predict the shape of the molecule, right? And we also understood that lone pair interactions are greater than lone pair bond pair, and which is greater than bond pair interactions also. And then also we understood that multiple bonds should be considered as only single bonds, right? All these are clear. So now based on this, by calculating the total number of electron pairs, how you can calculate or how you can predict the shape of molecules, we are going to discuss. So first we are going to discuss about the geometry or the shape of the molecules containing only bond pairs. There are no lone pairs in this case. Yes, when lone pairs are included, the scenario will be different. So even that we'll discuss in this session. So first we are beginning with the geometry of molecules with only bond pairs. Yes, now one more thing that you have to remember is geometry and shape. Yes, these are 2 different words and they are totally different terms as well, right? So we'll be using geometry and shape of the molecule in this session. So in the case of molecules having only bond pairs, right, the geometry and the shape are the same. But if lone pairs are also included, then geometry and shape will be different. Right? So you have to keep this in mind. So beginning with the first one, yes, let's take the example of BeCl2, right? BeCl2, right? So we know that, right? So how many valence electron Be is having, right? Only beryllium is having only 2 valence electron, right? And these 2 valence electrons are taking part in the bond formation. Right. So as you can see here in BeCl2 molecule, yes, 2 bond pairs are there. Yes, the one is forming a bond here, one is forming a bond here. Only 2 bond pairs, and around the central atom, are you able to see any lone pairs? No, right? Lone pairs are present in chlorine atom, but that we are not considering. Only around the central atom you have to consider, right? So, around the central atom, no lone pairs, only bond pair. So, how many number of electron pairs are there? Yes, bond pair is 2. That means a total of 2 electron pairs are there. Right. So, now a total of 2 electron pairs are there. So, what do? They have to attain a position in which the repulsion is minimum and the distance is maximum. So, 2 people are there. Yes, if they have to attain a position which is as maximum as possible, what do? They try to stand in a position opposite to each other, right? They won't come and stand here like this. What do? They stand here, right? So, what happens when these only 2 electron pairs are there? They attain a linear shape. So, that is BeCl2. So, understood? Only if 2 electron pairs are present, yes, what do they try to do? They try to attain a position which is as maximum as possible. Yes, the distance should be maximum. So, they obtain a linear shape. So, as you can see here in the BeCl2 molecule, right, the shape will be linear. That means the angle between the 2 bonds will be 180 degree, right? Yes. Now, moving on to the next one, right? That is, let's take the example of BF3, right? BF3 molecule. B, 1F here, 1F here, and 1F here, right? In this case also, what you can see, right? Are there any lone pairs? No, right? And how many electron pairs are there? Bond pairs are there? Only bond pairs, right? So, 1, 2, and 3. 3 electron pairs are there. So, if there are 3 electron pairs, yes, the molecule tends to obtain trigonal planar shape, right? All the 3 bonds will be in the same plane in a triangle shape. Hence, trigonal planar geometry. And the shape will also be the same. As I said, only bond pairs, right? So, trigonal planar will be the geometry. Clear for BF3 molecule, right? Now, moving on to the next one. That is 4 electron pairs, right? In the case of CH4 molecule, this happens. That is, the geometry or the shape is called as tetrahedral, right? If the electron pairs is 4, as you can see here, CH4, right? CH4. As you can see here, there are 4 bond pairs and no lone pairs. So, the total number of electron pairs is 4. So, the shape or the geometry that the molecule or the electron pairs try to attain is to eventually attain a position where the repulsion is minimum and the distance is maximum is tetrahedral shape or tetrahedral geometry, right? So, this is the tetrahedral geometry as you can see here. Yes, the 1, 2, 3 bonds here and 1 on the top. Yes, now if 5 electron pairs are present, only 5 bond pairs are present and no lone pair, yes, the shape or the geometry of the molecule is trigonal bipyramidal. Yes, trigonal and bipyramidal. That means some triangle shape is there and bipyramidal. 2 pyramidal shape is also there. That means, yes, as you can see, let's take the example of PCl5. Let's take the example of PCl5, right? Okay. Now, these 3 bonds are present in the same plane. And yes, as you can see, it is in a triangle shape, right? And one will be on the top and one will be on the bottom, right? So, as you can see, if I am taking this as the plane, 3 bonds will be present on this plane. And one P and Cl bond will be here and one P and Cl bond will be here. So, 2 pyramidals, right? 2 pyramids are formed and one triangle shape is formed. So, trigonal bipyramidal. Clear? Yes. Now, that is when only 5 electron pairs are present. Now, the last one is 6 electron pairs. This example can be taken as SF6. So, when only 6 electron pairs are present, yes, the molecule tries to attain, yes, octahedral shape or octahedral geometry. Right? So, in this case also, what is octahedral shape? Yes, 4 electron pairs or 4 bonds will be in the same plane and one in the top and one in the bottom. Right? So, that is octahedral geometry. Right? So, I hope it is clear. Right. Now, these are the examples that we discussed for only bond pairs. Now we are going to include lone pairs as well. So the shape will be different. I told you before, right? The geometry and shape will be different now. So now let's begin with the first example. Let's take the example of SO2 molecule, right? Yes. So as you can see, S double bond O, and a lone pair is present on sulfur atom, right? So how do you calculate the total number of electron pairs, right? Yes, there are 2 bond pairs here. Yes, we know that according to VSEPR theory, the multiple bonds are considered as single bond, right? So 2 bond pairs and 1 lone pair, right? So a total of 3 electron pairs are present, right? 2 bond pair and 1 lone pair, total of 3 electron pairs. So actually what should be the shape of the molecules? We studied, right? For 3, if the total number of electron pairs are 3, the shape or the geometry, yes, the geometry must be trigonal planar, right? The geometry is trigonal planar. But what is happening here? Even though the geometry is still trigonal planar, the shape is bent. Okay, the shape is called as bent. So instead of the molecule showing trigonal planar geometry, it is showing bent shape, right? The geometry will be the same, but the shape will be different. As you can see, yes, the shape is bent, like a V shape you are able to observe here, right? A V shape, yes. So such shapes are called as bent, right? Clear? So when there are 2 bond pairs and 1 lone pair, right? Yes, 2 bond pairs and 1 lone pair. The shape is bent, but the geometry is trigonal planar itself. Let's take the example of water molecule, which is very familiar to us, right? Yes. So as you can see, H2O, right? Yes, H2O. And on the oxygen atom, there are 2 lone pairs as well, right? Yes. Okay. Now, as you can see here, what are the total number of bond pairs there? 1 and 2. 2 bond pairs and 2 lone pairs. So total number of electron pairs is 2 plus 2, that is 4. So even that we studied. If the total number of valence electron pairs are 4, that means the geometry must be tetrahedral, right? It must be tetrahedral. But the shape is bent. Again, it is bent and not tetrahedral, right? Because lone pairs are also present. Now, why exactly they are differing from this geometry? Yes, if the geometry is tetrahedral, then the shape also must be tetrahedral, right? But when lone pairs are present, yes, the shape is becoming bent. Why it is that? So as you can see here, now lone pairs are also present. And here bond pairs are also present. So when we were studying about the different postulates of VSEPR theory, we discussed that yes, lone pair interactions are greater than lone pair bond pair interactions, and which is greater than bond pair repulsions, right? So now there are 2 lone pairs present here, right? Now these 2 lone pairs will repel each other, right? So a change in shape will be there. Now what will they try to do? They will try to attain a maximum distance from each other. So the bond will start bending, right? And now that will be between these 2. Now the lone pair and bond pair will also have an interaction, right? A repulsion will be there, and these 2 bond pairs will also have a repulsion between them, right? So all the 3 types of repulsions are having there, right? So we studied that lone pair interactions or repulsions are the maximum. So what these 2 lone pairs try to do? They try to reach a position which is maximum distance from each other, right? What happens to the bond? It starts bending, right? Yes, the 2 OH bond comes closer to each other, right? So that is what you can see here. So instead of tetrahedral shape, what happens? The bent shape is obtained, right? Yes. So actually in tetrahedral geometry, the angle between the bonds must be 109.5 degree, right? This must be the angle. But in water molecule, what happens is, because of this lone pair, bond pair and bond pair interactions, the angle reduces to 104 degree. Clear? Yes. So that is why the bent shape is obtained. I hope it is clear. Now moving on to the next one, that is ammonia, right? Ammonia, as you can see, there will be 3 bond pairs and 1 lone pair on the central atom, that is nitrogen, right? So 3 bond pairs and 1 lone pair means a total of 4 electron pairs. Now again the geometry must be tetrahedral, right? If 4 electron pairs are present, the geometry must be again tetrahedral. But no, because a lone pair is present, what you can see, this lone pair and bond pair, right? They start repelling each other, right? Only one lone pair is present, right? So there is no lone pair interaction. Now lone pair bond pair interaction is more. The repulsion is more, we know that. So what happens? Yes, this bonds try to come closer, right? Understood? The two NH bonds on the side will try to come closer because they want to repel from the, yes, maximize the distance from the lone pair. So the angle decreases again. Clear? So now what happens? The shape is called as trigonal pyramidal, right? So when 3 bond pairs and 1 lone pair is present, the shape will be trigonal pyramidal even though the geometry is still tetrahedral. So in this case also, it was actually supposed to be 109.5 degree, right? Yes, as the angle, that is the bonds are coming closer, what happens? Now the angle between them will be 107 degree. Instead of 109.5 degree, it is becoming 107 degree. Yes, I hope it is clear. So now let's move on to the next one. Let's take the example of ClF3 molecule, right? So as you can see, ClF3, right? And there will be 2 lone pairs as well, right? 2 lone pairs, right? We know the number of valence electrons in chlorine is 7, right? It is 1, 2, 3 which is taking part in bond formation, right? And the others will be present as lone pair, right? Yes. So as you can see here, yes, 3 ClF bonds are there, which are the bond pairs, and 2 lone pairs are also present on the central atom, right? So as you can see here, 3 bond pairs and 2 lone pairs, right? So a total of how many electron pairs are there? 3 plus 2, that is 5 electron pairs. So we have already discussed this. When there are 5 electron pairs present, what is supposed to be the geometry? It should be trigonal bipyramidal, right? But the shape now is called as T shape. Why? Because the lone pairs that is present here, what did we study? The lone pair interactions, and there are bond pair repulsions, and there are lone pair bond pair repulsions, right? So what happens? This lone pair and lone pair will start repelling each other, right? And the lone pairs and bond pairs also repel each other, and the bond pair and bond pair will also repel each other. So finally, after all this repulsions takes place and they try to attain a maximum distance from each other, so they are stable. So now the stable shape for them will be the T shape. So why it is called T shape? As you can see this part, right? It is like a T, right? This part you can see it is like a T. Hence it is called as T shape. So the total number of electron pairs, it is 5. But still, the geometry is trigonal bipyramidal. Still, the shape is T-shape because the lone pair interactions are greater than lone pair bond pair interactions, which is greater than bond pair repulsions. Okay. So, because of this repulsions taking place, they try to attain a shape which is stable for them. Right. Now, let's take the next example of SF4 molecule. So, it is S, then 4 SF bonds are present here, right? And then there is 1 lone pair. The number of valence electrons in sulfur is 6, right? So 1, 2, 3, 4, 5, 6. Total of 6 electrons are present, out of which 4 is taking part in bond formation. And this is present as lone pair, right? So a total of 4 bond pairs and 1 lone pair is present, right? 4 bond pairs and 1 lone pair. Again, the total number of electron pairs will be 5, right? So the geometry will be again trigonal bipyramidal, right? But the shape, because of the, yes, as you can see here, lone pair bond pair interactions will be here, as well as bond pair repulsions will be also there, right? There is no other lone pair, so lone pair interactions won't be there. Here lone pair and bond pair repulsions are there. right? So because of that, this is the final shape that the molecules having 4 bond pairs and 1 lone pair try to attain. So it is called as, the shape is called as seesaw, right? Why it is called as seesaw? If I'm considering this particular image here, I am just inverting in this particular line. I am drawing it here, and these 2 bonds that you can see, if I draw like this, does it look like a seesaw now? Yes, if 2 people are going to sit here, you imagine, yes, it behaves like a seesaw, right? So hence the name seesaw, right? So what you can understand from this, if there are 4 bond pairs and 1 lone pair, yes, the geometry will still be trigonal bipyramidal, but the shape will be seesaw now. And an example for it is SF4 molecule that we have discussed here, right? So what exactly you have to keep in mind here? Yes, when the lone pairs are also present in molecules, the shape and the geometry will differ, right? Yes, why it is? It is because of this lone pair bond pair interactions or lone pair bond pair repulsions that is happening here, right? So if 2 or more lone pairs are present, the repulsion with that will be the highest. Within that will be the highest, right? So because of these repulsions that is written down here, that is lone pair, lone pair, lone pair, bond pair and bond pair repulsions. Yes, because of this happening, the bond pairs and lone pairs try to attain a position where there the minimum repulsion and maximum distance will be obtained, right? Hence, the geometry and shape will be different when lone pairs are also present. Yes, I hope it is clear. Now, moving on to the last section, that is 4 bond pairs and 2 lone pairs. Let's take the example of XCF4, right? XCF4, right? And yes, we know that there are 2 lone pairs as well here. Yes, how many valence electron there are in xenon? It's 8, right? So 1, 2, 3, 4 are taking part in bond formation and the other 2 are present as lone pair, right? So a total of 4 bond pairs and 2 lone pairs are present in XCF4 molecule, right? Yes, so 4 bond pairs and 2 lone pairs. Yes, so the geometry will be again, right, octahedral. Yes, when the total number of electron pairs is 6, we studied that the geometry is octahedral, right? But what will be the shape now? It is square planar, right? Due to the lone pair bond pair interaction that is happening here, what happens? Right, the shape will be differed from the geometry. Due to the repulsions which is happening here, now the shape that they attain is called as square planar. Right? It is in a square shape, right? As you can see here. A square you can see here, right? And it will be all in the same plane. Hence, square planar. Clear? Right. Now, last one, right? That is, now moving on to the last one. That is 5 bond pairs in 1 lone pair, right? Let's take the example of BRF5 molecule. 1, 2, 3, 4 and 5 is here and a lone pair of electron, right? What is the number of valence electrons in bromine? It is 7, right? 1, 2, 3, 4, 5, 6, 7, right? That means 5 of it are taking it in bond formation, right? And the other 2 are present as lone pair. So, 1, 2, 3, 4, 5, 5 bond pairs are there and 1 lone pair on the central atom. So, 5 plus 1 is 6. Again, what must be the geometry here? It must be again octahedral geometry, right? But what is happening? The shape is becoming square pyramidal due to the, as you can see here, the lone pair bond pair interaction that is happening. What is happening? Because of that, the shape is becoming square pyramidal. So as you can see here, a square shape is visible, right? And on the top, the BRF bond on the top, one will be present on the top, forming a pyramid, and the lone pair will be present on the bottom. So you can imagine, right, a square and on top of it a bond is present. So hence square pyramidal. So 5 bond pairs and 1 lone pair is present. The shape will be square pyramid, even though the geometry is still trigonal planar. So till here what we have discussed, I hope it is clear for you. Yes, so the geometry and shape will be the same if there are no lone pairs. If only bond pairs are present, right, we understood what are the geometries, right? For 2 bond pairs, 3 bond pairs, 4, 5 and 6 we studied. Right, in those cases, lone pairs weren't there. Then we studied about the different scenarios in where lone pairs are also present. So even though the geometry will be same, the shapes become different due to, yes, the lone pair and lone pair bond pair and bond pair interactions. So as I said, the lone pair repulsions are more than the lone pair bond pair repulsions, which is greater than the bond pair repulsions. The molecules are attaining different shape. So I hope now if a molecule is given to you, by calculating the total number of valence electron pairs, you will be able to predict the shape of the molecules. Let's quickly do one example of BeH2. Okay, a molecule is given to you. How do you predict the shape of this molecule? Right, we know that BeH2 means two bonds are here, H and H. Two bonds are here. And we know that beryllium, total number of valence electrons is 2. So, one here, that is, it forms two bonds, right? So, a total of 2 bond pairs are present, right? And are there any lone pairs? No, right? On beryllium, there is no lone pair. No lone electrons are there, right? So, only 2 bond pairs, that means the total number of valence electrons pairs is also 2. So, what is the shape and geometry when there is only 2 bond pairs? Right, it is linear shape, right? It will have a linear shape and the angle will be 180 degree. We know that if it is linear shape, the angle will be 180 degree, right? So, I hope by this way, you will be able to predict the different shapes of the molecules using VSEPR theory. Now, we are going to see about the limitations of VSEPR theory, right? Even this had its own limitations, right? It fails for isoelectronic species. Right? What is isoelectronic species? Those atoms or ions which are having the same number of electrons, right? So, it fails for isoelectronic species. For isoelectronic species, the shape of such species were not able to be predicted, right? And it fails for transition metal compounds, right? Transition metal compounds, the shapes of those were not able to be predicted. It's not based on quantum theory. That is another limitation of this theory. It was not based on quantum theory of atom, right? And the last one, it could not predict the nature of the molecule. Even though it could predict, that is VSEPR theory could predict the shape of the molecule, it could not predict the nature of the molecules. So these were the few limitations of VSEPR theory. So I hope what we have discussed is clear for you, right? So in the next session, we are going to discuss the next theory, that is valence bond theory, or in short form, you can call it as VBT, right? Valence bond theory, under which we will be studying in detail about the directional properties of the bonds and the types of overlapping and nature of covalent bond, right? In VSEPR theory, we only studied about the shape of the molecules, right? But in VBT, that is valence bond theory, now in detail we are going to study about the nature of the bonds as well. So in the next session, we will be discussing in detail about valence bond theory. So I hope what and all we have discussed in this session is clear for you. So that's all for today. Thank you.